Welcome to homework.
So we want to know between the photons emitted by a UV lamp and a TV emitter, which have a greater wavelength, frequency, energy, and momentum. To answer this question, I'm going to be considering them as electromagnetic waves, which they are, and they're going to have shapes similar to the waves you see at a beach, but more consistent and regular than I can draw them. When we refer to the wavelength, we're referring to the distance between two peaks or two troughs, just two of the same feature on adjacent waves. And from just this information, we can actually tell which waves have a higher frequency, energy, and momentum. And to explain how, I'm going to ask you to imagine yourself as standing on the waterfront at a beach. And you're going to get hit by different kinds of waves. And electromagnetic waves, so photons, actually have a constant speed regardless of their wavelength. So back to the beach analogy. You're going to be standing at the waterfront, and let's say you get hit by a really long wavelength wave, so a really large distance between two peaks. The frequency with which you will get hit by these peaks, that is the frequency that we're looking for in this question, is quite low because there's a lot of time between them. So there's few waves per second. With a short wavelength wave, you're going to have a higher frequency because there's very small time between waves because they're so close together and they're moving at the same speed as the long wavelength wave. So when you have a long wavelength, you have a small or a low frequency. That's a better way to put it. Whereas when you have a short wavelength wave, you have a high frequency. Now, we can also tell from the wavelength of the wave the energy that it carries. So imagine yourself standing at the waterfront or even bobbing in the water. When you get hit by a low frequency wave or a long wavelength wave, you're going to be lazily drifting up and down at a relatively slow speed. Whereas with a short wavelength wave, you're going to be whipped up and down every single time it goes up. And so you're going to be moving a lot faster. Now, when you're moving a lot faster, when you're vibrating a lot faster like that, you actually have a higher energy than when you're lazily, slowly drifting up and down, because the faster you're moving, the higher energy you have. So this has high frequency, but also high energy. Whereas a long wavelength wave with its low frequency has low energy. And finally, since you're moving slower, you're also going to have a low momentum because momentum is just a measure of your mass, which doesn't change in this scenario, as well as how fast you're moving, your speed. So both energy and momentum are low in long wavelength waves and high in short wavelength waves. So now we bring it back to the question at hand. In light waves, it works just the same way as waves on the beach. So all the photons in the universe, all the electromagnetic waves in the universe fall somewhere on the electromagnetic spectrum. And some have very short wavelengths like gamma rays. Some have very long wavelengths like radio waves. And in the case of the UV lamp, it's right there in the name. It's pretty obvious. It's UV light. Now, TV emitters actually use infrared to send signals to your TV. And a fun trick you can do is actually point it at your cell phone camera, take a video, and press a button on the TV remote. You'll actually see it flash in the camera, in the video, because digital cameras actually pick up on infrared. So the TV emitter is emitting an infrared light. So as we discussed earlier, at shorter wavelengths, you have higher frequency, energy, and momentum. UV is shorter than IR. So the UV lamp has higher frequency, energy, and momentum, whereas the TV emitter, which is an infrared, which is a longer wavelength, only has a higher wavelength.